Okay, last lesson of this unit, and again, it's another short one. We're going to talk about catalysts and how they impact reaction rates. So a catalyst is a substance that increases the rate of chemical reaction by giving it an alternate pathway with a lower level of energy required. So remember that activation energy is the energy that we need to get the reactants to move and interact with each other to create that new compound. And so, especially when we're looking at endothermic reactions where it requires energy for that reaction to go in the forward direction, uh, oftentimes that is a cost um, an increase in cost. It's not cost effective. That's the word I'm looking for. And so when they add a catalyst in, it lowers that amount of activation energy to get that reaction started, and we can get that reaction to go forward with a less amount of energy. And so what happens is the catalyst binds to the reactants and it aligns them so that they will react, and it speeds up the reaction rate, which gives a greater yield of product. So you're using, instead of using a quarter of the reactants, now maybe you're using 75% of the reactants. Again, therefore you're requiring less reactants because you're getting more products. And so that's cost efficient. And catalysts aren't consumed in the reaction. So when that reaction happens, the catalyst ends up being released and it goes back into the reaction and keeps working with all of the unreacted reactants. Having said that, eventually that catalyst will run its life course. And so then you would have to add fresh catalyst, but it's definitely a cost saving measure. The flip side to that, and I've been a while out of industry, but when I was in industry, most catalysts are not environmentally friendly. So there's a bit of a trade-off. We can get more reactants that require less energy, require less input of reactants, and maybe those reactants are super not environmentally friendly. So there's always a trade-off. There's a risk-benefit factor that we always have to look at when we're looking at reactions that require a catalyst. That's something for you to keep in mind. So potential energy diagrams help to explain how a catalyst works. And so even though the catalyst increased the reaction rate by giving it an alternative pathway, this delta H does not change. Okay? The delta H for the reaction does not change. And so this is what it would look like. This is our potential energy in kilojoules. This is our reaction coordinates. And so if we look, let's look at a so here, let's say that this requires a big jump of activation energy to get to the products. And so this is our activated complex. Okay. From here to here, from reactants to products, this is our delta H. This we see as being our, remember, from our reactants up to our activated complex, this would be our activation energy further forward. Now, if we were to add a catalyst in there, what happens is the catalyst binds with the reactants and it lowers the activation energy. So maybe it does this kind of pathway. Okay, and so from the reactants up to here, so now this is kind of our new activated complex. This is our new activation energy of a catalyzed forward reaction. Okay. Now, where do we see this in real life? Well, lucky you guys are in Bio 30. Enzymes. Enzymes are in our catalysts in the living systems. We see amylase. Amylase is used to help break down starches in our mouth. We see lipase. Lipase is used to break down fats. We see lactase. Lactase is an enzyme used to help break down milk. So if we didn't have access to these enzymes in our body, and these are true real life diseases, not necessarily genetic or hereditary. Sometimes it's through genetic miscoding. But people don't have these enzymes, and so they absolutely cannot break down starches. The carbohydrates are death to them, or they can't break down fats, so fatty foods. And fatty foods are milk or sour cream or cheese, meats, those kinds of things. They can't eat those. Or amylase, lipase, lactase, they can't break down milk products, and then they end up with a deficiency. And so these are real life-threatening things. And so enzymes are crucial in our bodies. The other one is protease, which helps break down proteins. That's a very common miscoded genetic issue. Another one that we look at in Bio 20 is chlorophyll, is a catalyst that speeds up the reaction of splitting the water molecules into oxygen and hydrogen ions so that we can get that release of that electron in the electron transport chain. So all these things that you learned in Bio 20 and Bio 30, they cross over into chemistry, and now we're starting to see why there's a field of biochemistry out there. Catalysts are important for environmental and economic reasons. I talked about those at the beginning of the lesson. Catalysts are used in exhaust systems, catalytic converters. Usually they're made out of platinum. Platinum is a precious metal, and so that's why catalytic converters are being stolen out of vehicles. But that catalytic converter helps break down those exhaust gases during combustion, which allows for more power. And so we also get less harmful fumes released to the atmosphere. And by using a catalyst, we use less activation to start the reaction, which on an industrial level, it saves money. You look at Weyerhaeuser or the big plant, Dunvegan gas plant, they all use a catalyst in some form. They use oxygen scrubbers to help break down oxygen or sulfur. It's all throughout their whole processes. And it's, again, that risk benefit factor that all businesses and the medical field and the environmental field have to weigh the pros and cons of. So you're going to pause it here. You're going to work on question 418, number 1, 2, and 6, and page 420, 7, 8, 10, 14, 15, and 19.